Varun Acharya from Equinox. So in this session, we will be having a session on finding imposter among us, container edition, and where Varun will deep dive inside the spaceship of containers to find the imposter with the help of crew members. So I guess a quite interesting topic.
So hey everyone, I'm Baran, and thank you for joining me on my session of Finding Imposters Among Us Container Edition. A little bit about myself. I'm Barun Acharya. I am a maintainer of CubeArmor, a CNCF sandbox project. I work as a software engineer at Equinox. I've been associated with open source programs like Google Summer of Code, Linux Foundation mentorship, both as a mentee and a mentor. I hang out at open source developers community, which is based in our college JIIT. And I'm not a student anymore. I recently graduated. Pretty excited about that. So, since it's KCD Kubernetes Community Days, our main focus of our workloads is containers. I'm assuming everyone here knows about containers. But with the rise of adoption of containers, so has risen the cyber attacks on the same. Like recently, Ram today talked about Log4j. And attacks similar to that are increasing the demand for enforcing security on our containers. So attacks like 0 days, evasive malware, privilege escalation attempts, these happen at runtime. We cannot really detect it with static scanning because these are unknown unknowns. We can never predict when these can happen and when a new vulnerability pops up and it is to be exploited by any attacker. So how do we deal with vulnerabilities that manifest at runtime? We deal with them at runtime. Hence, container runtime security. A quick question, anyone here or folks here are implementing some form of runtime security or have heard about runtime security earlier? Great. So to abstract away the complexity, I compiled container runtime security into 3 parts. First is detecting the malicious activity. It involves monitoring and observability. Alerting the activity with context, where the malicious activity happened, which container, and details like that. And finally, trying to prevent it. But before I dive into the technicalities of how it can be achieved, I want to take you on a galactic space journey. How many of you have played the game Among Us here? Nice, some of you. It was pretty crucial for me in my lockdown, passing my quarantine with playing this game with my friends. So I thought I'd take the example of Among Us and explain you like how Among Us intervenes with the realm of container runtime security. So once upon a time, in a distant galaxy, there was a bustling space station where crew members worked diligently on their assigned tasks. This space station was critical hub for intergalactic trade, and its smooth operation were vital for the prosperity of the galaxy. However, there was a hidden danger. Imposters had, just like how in the game, had sneaked into the galactic space station, disguised as crew members. These imposters had malicious intent and were determined to sabotage the station's operations. They could sneak into any area, bypass security measures, wreak havoc the infrastructure. To combat this threat, the crew members realized they needed to adopt a security approach inspired by the concept of zero trust. They understood that trusting blindly in the identity of their colleagues, just like assuming every crew member was genuine, was no longer sufficient. In the game Among Us, crew members relied on their keen observation skills to identify and eliminate imposters. Similarly, crew members on the space station began to applying various security principles to identify and contain potential threats within their containerized workloads. They realized that securing the supply chain alone wasn't enough, even if the crew members were initially verified and trusted. Ram today talked about how S-bombs can help us verify and how we can secure our supply chain. But even if things are initially verified and trusted, there was still a possibility that threats could emerge at runtime. It was not a question of if, but when the imposters would strike. The understanding that containers were not impenetrable fortresses, the crew members embraced the power of runtime security. They continuously monitored the activities within the containers, and they would scrutinize the actions of their fellow crew members in the game. To achieve this, the crew members utilized advanced profiling. They keenly monitored and analyzed various activities happening inside their spaceship. And as soon as something malicious happened, they would call for an emergency meeting. Armed with this knowledge, the crew members enlisted the help of various underlying primitives like eBPF and LSM, which we will dive after this analogy. These security mechanisms acted as their trusted crew members, assisting in identifying and quarantining breaches at runtime. Just as crew members in Among Us would use emergency meetings and voting systems, the crew members leveraged these tools to isolate and neutralize threats within their containerized environment. So, finally, by implementing these practices, they had triumphed over the imposters, restored peace and prosperity in their galaxy. And so the story spreads across the galaxy, serving as a testament to the power of zero trust security and vigilance required to identify the imposters among us, whether in a game or in the realm of containerized workloads. So coming back to container runtime security, now that I had created an analogy, let's dive deep into how we can implement this, like how the space crew implemented runtime security in their spaceship, how we can implement runtime security in our own containerized workloads, be it in Kubernetes, be it unorchestrated containers that you are running. But it's important to understand that containers are not a black box. Like containers within themselves have a lot of crew members. We need to profile and understand the entities inside our containers as well. Even if the containers are a sandbox in themselves, they have access to outside configurations as well. Like containers have access to various Linux capabilities. They try to network with peer containers using over network. And they have access to volume mount points where various configuration file and secret data are stored. But what if a malicious binary now sneaks into this container somehow? Assuming there's a vulnerability in our supply chain and a malicious binary has sneaked into our container somehow. Now this malicious binary will have access to all these mount points, capabilities, and network. So we need to profile our containers in their entirety so that when a malicious binary sneaks in somehow, we know that it's not an intended action and we can deny it then and there only, preventing any further damage to our infrastructure. So how do we go about detecting and alerting this malicious activity? What happens is, when a malicious activity happens, it triggers a lot of kernel events. So we can hook onto these kernel events to understand what's happening and alert it to the user that, okay, something is happening and here's a context, a telemetry event for you that, okay, you need to look into it. But kernel events in themselves are not enough. We cannot really understand and decode the kernel event on its own. We need to understand, we need to get the context as well that, okay, this kernel event happened, but it is associated with which container, which cluster. We are on infrastructure at scale, there are thousands or tens of thousands of containers running at once. You cannot really identify a kernel event where it happened. So we combine the kernel event with container runtime data and orchestrator data. But how exactly do we go about hooking onto these kernel events? There we have eBPF. eBPF is a trusted technology that has been in use now and has been key to various cloud-native observability projects today. It provides us with a safe, programmable, and performant way to hook onto these kernel events and help us monitoring and alerting the observability data we are looking for. Now that we have covered detecting and alerting the activity, let's talk about how can we take action on it. There are primarily two ways that we can go about taking action on a malicious activity. Either once the entire cycle has happened, the detection engine alerts us with the information that, okay, malicious activity happened. We have some manual security operator or an automated way to go ahead and kill the process. And that's how we can contain it. But by the time this entire life cycle happens, the malicious activity could have caused much more danger because the entire pipeline takes time. Going from kernel to user space, combining the information, goes to some automated or manual system, and then it's killed. The other idea of enforcement is inline enforcement. The kernel itself is responsible for denying the malicious activity as soon as it's detected. But how can we do this? What are the Linux primitives out there which can help us with implementing this inline security, inline enforcement? A couple of them are LD preload, Seccomp, and Linux security modules. LD preload provides us with a user space control, and since each and every application out there goes through a user space syscall, and then only the kernel events are triggered, we can override these libraries and have a custom layer upon it to help us with the enforcement of security. But the problem here is that, for an example, let's take an example of Go applications. Applications built on top of Go are statically compiled, and they don't really use the dynamic libraries. They contain the libraries in themselves only. So they can bypass this modified library and go ahead and access the system calls on kernel. So we cannot really have LD preload help us with enforcing security across all the system. Then we have Seccomp. Seccomps help us with sandboxing using various filters, and it has native integration with Docker and various container runtimes as well. But the issue is it has very limited filtering options. Finally comes Linux security modules. These are mature ecosystem of hooks, which has been in Linux kernel for around more than 2 decades now. And they handle a lot of vulnerable timelines like time of check and time of use. But the issue here is that they are not integrated well enough with the container ecosystem we have today. They were built for like host applications which were running over the Linux kernel directly. We will see an example later how exactly, what's the issue with how the output looks like and what could we have more. But now that we have talked about these primitives, how do we exactly integrate them with our cloud native workloads? We have the Kubernetes pod security context with us. A security context defines privilege and access control settings for a pod or container. And this includes, but not limited to, Seccomp, AppArmor, SELinux. AppArmor and SELinux are a kind of Linux security modules only, which will help us secure our containers and help us prevent this malicious actor. Starting with Seccomp capabilities and SELinux, we can define them this way, but the issue is that they treat the entire container as a single entity itself. But I talked about the importance that how we need to profile entities inside our containers as well. And that's where these security primitives lag, because they treat the entire containers as a single entity, and the rules are enforced across the container. Then we have AppArmor. AppArmor does provide us with the fine-grained access control, like we can block access to various system paths here, like whether it should be read, write, a fine-grained access control we have. But the issue is the output that we receive, like suppose a malicious actor now has sneaked into your system and it tried to access your password. We do receive the alert that, okay, cat tried to access the password file, which should have been denied and is denied, but we don't have the context in which container did it happen and who tried to access it, which cluster. A lot of information is missing here, which is important to us. So the problem statement I came up with is we need access control over our container entities. We need a declarative way to manage our policies for access control such that I can declaratively say that which containers need to have which set of policies. We need to have inline policy enforcement. I already talked about the issues with async enforcement. And finally, we need the telemetry events with context. A couple of cloud-native tools today which help us with this are kubearmor, Tracy, Falco, Tetragon. All of these are CNCF projects only, and they are using eBPF for monitoring and help us with the observability side of aspects. But the issue comes with enforcing when the malicious activity happens, how exactly do we prevent and take action on it? Tracy, Falco, Tetragon here take the approach of post-attack mitigation. They go ahead and stop the container or send a signal after the event has happened and something in line of that. But we have already talked that with this, there could be a gap which could be exploited by the attacker. Here comes kubearmor, which leverages Linux security modules for helping us with inline mitigation. Talking about kubearmor more, it's a cloud-native runtime security enforcement system that restricts the behavior, such as process execution, file accesses, network operations of the containers at the system level. Let's see how kubearmor does it under the hood. We have the malicious activity happening inside our container. As I said, these do trigger events inside our kernel. So we have eBPF probes, Linux security modules, which listen to policies, and kubearmor hooking onto these probes and LSM to help us with the enforcement aspect of things. And then it combines the information with container runtime orchestrator, finally completing the lifecycle of helping us with enforcing our cloud-native infrastructure. Once we receive, I will show you a demo example policy in our demo a few minutes later. But what happens is when kubearmor receives the alerts policies, it converts it into the AppArmor profile which we discussed earlier. But now, once the enforcement is being done by the LSM here, kubearmor listens to eBPF probes to help us with the activity with context. Like it will tell you which container it is happening, what was the PID, what exactly the command was executed. Handles a lot of edge cases which should help you with the security of your system. So let's check kubearmor in action. Some details about the demo scenario which I will use. We have a container here which has access, which has a mount where it stores its secrets. And I will showcase how we can allow specific entities and deny the rest. It will mostly involve around how we can lock down access to pod data, secret storage, etc. Cool. So I have this Vault container here. Vault is a secrets management by software by HashiCorp. Anyone here using Vault out there? Nice. So what I have here is a policy to help me with enforcement on Vault. What happens is Vault stores all its data inside a directory called Vault. And it has the secrets it has is stored inside, and various configuration files are inside this folder itself. Ideally, inside a container, this folder should only be accessed by the Vault binary itself, because it's the only binary out there which is responsible for managing all the entities inside our container. So here we have a policy to block access to Vault directory in general, but then allow the access to Vault directory by the binary Vault binary only. So let's try to, so I have this policy applied already. I hope the terminal is visible to you all and you can read it. Now if I go ahead and do, I can access this file all right because my policy is only contained to the vault directory itself. But what if I go ahead inside vault and now try to access any file inside it? I get a permission denied here. And we have all the information here that, okay, the container name was vault, it was inside container ID this, the pod name was this, namespace, a lot of information out there, which should help us identify if someday vault is being under attack. It has all the context that, okay, this is how the attack, this is where the attack has happened, and this is the context for you. But since I talked about inline mitigation, it's not that once you receive the event, then the enforcement is done. The enforcement and the alert happens at the same time. So there's no security gap to help exploit this. You might ask even if someone is able to access the vault directory here, it's encrypted. Why would someone try to access it? Because what would someone gain from accessing the vault directory if it has encrypted data? But what if out there some attacker tries to add another layer of encryption over the vault directory? Then you yourself are not able to access the vault directory as well. And that's how ransomware attacks work. They will ask you for ransom to help you before they start decrypting things. So that's why we need this fine-grained access control, that who all can access, who should be able to access this. So Cube Armor solves the problem statement that I talked about. And that's all from me. Thank you. You can check out Cube Armor at cubearmor.io. I am Barun Acharya, go by Demon1024 over the internet. You can reach out to me and know more about me at barun.cc. Any questions right now, since we have a lot of time left? Can you be a bit?
I just wanted to know what is the footprint it will require on infrastructure layer. Let's say if I'm running this in Kubernetes cluster or VM, there will be certain requirement in terms of memory or CPU. And that requirement may grow over the time when infrastructure is very big. Maybe thousands of VMs we are talking about. What is the requirement like? Is it minimal overhead or?
It is minimal in the way, like we have benchmarked it with, I guess, Redis. We try to secure Redis. And the overhead which we saw over the Redis benchmark was less than 3%. I know 3% is not as the infrastructure grows, it's still a considerable amount, but that's something you need to bear with since it is enforcing at such granular level. Kernel, you get thousands or tens of thousands kernel events in a minute or so. And trying to profile it and enforcing things at that layer does come with a cost, but it's less than 3%. And that is something which I have talked to users out there, and they have said that it's all right for the use case it's solved.
Do you have open benchmarks ready on CubeArmor website?
Yes, it's on in our wiki. The benchmark is there.
Thank you.
Hi, Varun. So when you say it prevents, so does it completely prevents, or if any data is compromised, what are the steps here? Or it never happens? The container data, before it prevents, if there is any compromised data, what do you do of that?
So how CubeArmor works is it's a rule-based engine, right? So how we say is that, like, you create, so whatever all is happening inside your container, you profile them beforehand. And there's a rule set out there which is generated from that. And any deviation from that rule set is denied. We are not saying, it's not that we are mitigating, we are identifying malicious actor like that. The malicious actor is any deviation from the original scope of your application is detected as a malicious event. So any deviation from that original scope of your application is detected as a malicious event and is contained there. Sorry. Yeah. Yeah. That, yeah. But that's why I said like CubeArmor didn't reinvent a wheel of inventing a new security mechanism. LSMs have been proven as a safe mechanism to enforce things from around 20 plus years, and it is trusted, and CubeArmor builds on top of that, and that's why we can say that it's. But any like someday if a vulnerability pops up in LSMs, but today, as of now, we don't think that that's happening.
So my other question is it's kind of a silly question, honestly.
That's right.
But CubeArmor takes care of malicious activities within a container or a pod, right? It takes care of, within a container or a pod, it takes care of these kind of malicious activities or imposters from happening, right? My use case comes from a more abstract level of things. So secrets are already namespace scoped, right? But I want to scope them to pods as well, specifically to pods, wherein would CubeArmor be capable of, or not, if not now, then in the future, to create these kind of policies wherein a particular secret within a namespace would only be accessible by a particular pod, or even not even by a particular pod, just by a particular container within the pod or something like that. Because where I come from is, we have a lot of open source pods running with a few of our proprietary ones as well, right? And secrets are accessible. Pods can go ahead and access them, without any issues if they're located within the namespace. So would there be a way eventually down the line to restrict these kind of accesses as well?
I do think wouldn't that be since it's a pod-to-pod communication, secrets would be let's say that secrets is another pod. It's a different Kubernetes object, but it's a different, let's call it a pod for now. Since it's pod-to-pod communication, can you not just set up a network policy saying that, okay, the specific pod is not allowed to access these set of secrets, or the service account that the pod is using to access the secrets is contained to not able to access that particular secret file?
No, so where I'm coming from is, if it still tries to do that. So this is about preventing. It's already prevented, but it's about detection.
Right. So I am not able to, I don't think CubeArmor fits here because it's supposed to, it's not interpod, it can help, since it works based on the primitives like process, file, network, entities running inside the container, it would see, you could have policies on your pod, what all IP it is allowed to access, and policies on the secret end, where the incoming traffic comes from. That's how CubeArmor can work, having separate policies on both the pods. But identifying the entire workflow, I don't think that will be in our roadmap today. But if you could if you could open an issue on our GitHub, we can maybe discuss it further. Maybe there's a way that serves the use case. As of right now, I cannot think of it.
Right now, it's not a threat because people have not thought to that level. But yeah, eventually, when you
it can be in the roadmap. Yeah. That's why I said please reach out to us on Slack or GitHub. We can discuss it. Okay then. Thank you, folks. I will be around this event. I am till the evening. Say hi to me, talk about runtime security, open source in general. Happy to talk with you. Thank you. Bye-bye.
Yeah, Barun. Great session overall. To explain the slides in a little bit gamified version. So I hope the audience was able to relate that well. Thank you, Varun.